Hey there, and welcome back to the Sleepless Scientist. Tonight, we're embarking on a journey not just through space, but through the very fabric of reality itself. We'll be chasing whispers of light, uncovering how its speed shapes our universe, and challenging everything we thought we knew about time and distance. But before we dive in, if you enjoy these quiet explorations, please consider giving us a like and subscribing. It truly helps us keep these stories coming. Now, settle in. Our story begins not in a bustling lab, but under ancient skies long before telescopes or equations. Imagine early humans gathered around a crackling fire, captivated by its dancing flames. Light was warmth, protection, and the key to seeing the world around them. From the sun's life-giving glow to the fleeting flash of lightning, light was a profound mystery. It arrived instantly, it vanished instantly, and it seemed to connect everything, yet remain intangible. It sparked the very first questions about existence. Philosophers, centuries later, began to formalize these ponderings. Was light a continuous stream, like water, or was it made of tiny, discrete bits, like grains of sand? How did it traverse the immense void between stars and our eyes? If light was a disturbance, like a ripple in a pond, what was the pond itself? Did the universe have some invisible substance through which light traveled, or could it move through nothing at all? These were profound riddles with no easy answers. Centuries of contemplation passed, each generation adding a new layer to the enigma. Then, in the late 17th century, a towering intellect stepped onto the scene, ready to bring order to the chaos of light. Sir Isaac Newton, a name synonymous with gravity and calculus, turned his keen mind to light. He wasn't just observing, he was experimenting meticulously in darkened rooms using prisms and lenses. Newton famously used a prism to split white light into a spectrum of colors. He then used a second prism to recombine them back into white light. This was a crucial observation, suggesting light wasn't simple. Based on these experiments, Newton proposed his corpuscular theory. He believed light was composed of tiny, discrete particles, which he called corpuscles, streaming from a light source. This particle model elegantly explained reflection. Imagine a billiard ball bouncing off a cushion. Light corpuscles, he reasoned, simply bounced off surfaces in a similar, predictable way. Refraction, the bending of light as it passes from one medium to another, was also explained. Newton suggested that as corpuscles entered a denser medium, they were pulled by an attractive force, changing their path. Each color Newton proposed corresponded to corpuscles of different sizes or masses, which traveled at different speeds or were affected differently by forces in media. Newton's theory was powerful. It offered a concrete, mechanical explanation for many observed phenomena of light, and his authority in the scientific world was immense. For a time, it seemed the riddle was solved. However, even as Newton's ideas gained traction, another brilliant mind, a contemporary, was developing a very different understanding of light's nature. Christian Huygens, a Dutch polymath, proposed that light was not a stream of particles, but rather a wave, an oscillation propagating through a medium, much like sound waves travel through air. To visualize this, imagine dropping a stone into a calm pond. Ripples spread outwards, but the water itself doesn't move with the ripple, it simply oscillates up and down. Light, Huygens suggested, behaved similarly. But if light was a wave, what was the medium it traveled through? Huygens posited the existence of a subtle, invisible substance permeating all space, which he called the luminiferous ether. Huygens' wave theory could explain phenomena like diffraction, where light bends around obstacles. Particles would cast sharp shadows, but waves could spread out as they passed an edge. It also offered a natural explanation for interference, where two waves can combine, either reinforcing each other to create brighter light or canceling each other out to create darkness. Despite its elegance, Huygens' wave theory faced an uphill battle. Newton's prestige was immense, and the idea of an invisible ether seemed less intuitive than tangible particles. For over a century, the particle view largely dominated. It was simple, it was championed by a giant, and it fit many observations well. Yet, the wave theory's quiet whisper of an alternative never fully faded. As the 18th century gave way to the 19th, new experimental techniques and a fresh wave of curiosity began to challenge established views. The stage was set for a definitive test. In England, a brilliant polymath named Thomas Young, a physician, physicist, and linguist, became intrigued by the debate. He saw a way to put both theories to a critical test. Young understood that particles and waves would behave fundamentally differently when encountering two narrow openings. This simple insight would lead to one of science's most iconic experiments. He devised an experiment where a single beam of light was directed towards a screen containing two very narrow, closely spaced slits. Behind this, another screen would capture the resulting pattern. If light were made of particles, Young reasoned, then passing through two slits would result in two distinct bright lines on the second screen, corresponding to the paths the particles took through each slit. But if light were a wave, a very different pattern should emerge. Each slit would act as a new source of waves, and these waves would interfere with each other, creating a pattern of bright and dark bands. With meticulous care, Young performed his experiment. The light source was a small hole illuminated by sunlight, ensuring a coherent beam. The slits were carefully cut, their separation precise. He dimmed the room, adjusted his apparatus, and observed the screen. What he saw was not two simple lines, but something far more intricate and beautiful. There, on the screen, was a series of alternating bright and dark bands, a classic interference pattern. It was unmistakable. Light was behaving like a wave. This was a profound moment. Young's double-slit experiment provided compelling evidence that light exhibited wave-like properties, seemingly settling the long-standing debate in favor of hydrogens. The bright bands occurred where wave crests aligned, reinforcing each other. The dark bands were where a crest met a trough, canceling each other out, a phenomenon only possible with waves. The scientific community, initially skeptical, slowly began to accept the wave theory of light. Young's elegant experiment was too clear, too undeniable to ignore. With the wave theory, phenomena like polarization and dispersion, previously difficult to explain, suddenly made perfect sense. It was a powerful, unifying framework. But the wave theory brought its own challenge: the ether. If light was a wave and waves needed a medium, then this mysterious, invisible ether had to exist throughout the universe. This ether had to be incredibly rigid to allow light to travel at such immense speeds, yet also completely permeable, offering no resistance to planets moving through it, a truly paradoxical substance. Scientists began to devise experiments to detect this ether, to measure its presence, or to observe Earth's motion through it. They were convinced it was there, just waiting to be found. For a while, it seemed the luminous riddle was largely solved. Light was a wave traveling through the omnipresent ether, a neat, elegant solution, yet a subtle unease persisted. The properties required for this ether seemed increasingly contradictory, almost impossible, and the experiments designed to find it kept yielding bewildering, null results. The universe had more surprises in store. The stage was now perfectly set for the next act in our story, where the very speed of light itself would become the central character, revealing truths far stranger and more profound than anyone had imagined. Join us next time as we delve deeper into this cosmic speed limit. The previous chapter left us with a paradox: the luminiferous ether, a substance required for light waves, yet seemingly impossible in its properties. Scientists grappled with this invisible, untouchable medium, a ghost in the machine of the universe. The elegant wave theory of light, so powerfully confirmed by Young, now carried this heavy, contradictory burden. It was a beautiful solution with an unworkable foundation. The universe, it seemed, still held a deeper secret. Perhaps the answer lay not in light alone, but in its connection to other fundamental forces. For centuries, electricity and magnetism had been observed, catalogued, and used, but their profound relationship remained largely unarticulated. Into this intellectual landscape stepped Michael Faraday, a man of extraordinary intuition and experimental skill, though without formal mathematical training. His genius lay in seeing the invisible. Faraday spent countless hours in his laboratory meticulously experimenting with electrical currents. He observed how they flowed, how they could be generated, and how they could produce heat and light. Separately, he explored the mysterious forces of magnetism. He mapped magnetic fields using iron filings, revealing the invisible lines of force that emanated from magnets, pulling and pushing without contact. The intuition grew that these two seemingly distinct forces were, in fact, intertwined. Earlier work by Oersted had shown that electric currents could create magnetic fields. Faraday felt there was more to discover. Faraday wondered if the reverse was also true. Could magnetism produce electricity? He began a series of experiments, often simple in setup but profound in implication. He famously discovered that moving a magnet near a coil of wire would induce an electric current in that wire. It wasn't the presence of the magnet, but its change in position, its motion, that mattered. This led Faraday to a revolutionary concept: fields, not just forces acting at a distance, but invisible fields of influence that permeated space, changing and interacting. An electric field that changed over time could create a magnetic field, and a magnetic field that changed over time could create an electric field. This was a dance, a profound and elegant interplay. Faraday, with his mind's eye, saw these fields not as abstract concepts, but as real, physical entities filling the space around charges and currents. They were the true actors. His groundbreaking insights, however, were often described in qualitative terms, through detailed experimental notes and conceptual models. The mathematical framework to truly capture their essence was still missing. The scientific world needed a way to translate Faraday's intuitive understanding into a universal language, one that could predict and quantify these interactions with precision. This is where James Clerk Maxwell entered the narrative, a Scottish physicist with a profound gift for mathematics, poised to weave Faraday's observations into a tapestry of unparalleled elegance. Maxwell took on the monumental task of unifying all known laws of electricity and magnetism. He sought to condense the sprawling body of experimental data into a few fundamental principles. He wasn't just describing phenomena, he was searching for the deep, underlying symmetries and relationships that govern the behavior of electric and magnetic fields. It was an act of profound intellectual synthesis. Over several years, Maxwell meticulously formulated a set of equations. These weren't just descriptions, they were predictive tools, expressing how electric and magnetic fields influenced each other and changed through space and time. Eventually, these efforts culminated in what are now known as Maxwell's equations, four elegant statements that encapsulated the entirety of classical electromagnetism. They were a symphony of cosmic forces. The first equation described how electric charges create electric fields, showing that these fields originate from positive charges and terminate on negative charges. It was the source of all electrostatic phenomena. The second equation revealed that there are no isolated magnetic poles, no magnetic charges like electric charges. Magnetic field lines always form closed loops, a fundamental difference from electric fields. The third equation formalized Faraday's discovery: a changing magnetic field creates an electric field. This was the mathematical heart of electromagnetic induction, powering generators and transformers. The fourth and perhaps most revolutionary equation combined Ampere's law: currents create magnetic fields, with Maxwell's own crucial addition: a changing electric field also creates a magnetic field. This addition, known as the displacement current, was a stroke of genius. It meant that even in empty space without wires or charges, a changing electric field could sustain a changing magnetic field. With these four equations, Maxwell had not just described electricity and magnetism, he had unified them into a single, cohesive force: electromagnetism. It was a profound simplification of nature. But the true magic of Maxwell's equations lay in an astonishing prediction. When he combined them, they didn't just describe existing phenomena, they revealed something entirely new. The equations showed that oscillating electric and magnetic fields could generate each other, propagating outwards through space as a self-sustaining wave. No medium was explicitly required. These were not sound waves which needed air, nor water waves which needed water. These were electromagnetic waves carrying energy and momentum through the vacuum itself. Imagine an electric field oscillating, which creates a magnetic field. That changing magnetic field then creates an electric field, which in turn creates another magnetic field, and so on. A dance of pure energy. Crucially, Maxwell's equations also allowed him to calculate the speed at which these hypothetical electromagnetic waves should travel. This was a purely theoretical derivation, based only on fundamental constants. When he crunched the numbers using the known values for the permittivity and permeability of free space, a remarkable number emerged. The calculated speed was approximately 300,000 kilometers per second. This was not just any number, it was precisely the known speed of light, which had been measured with increasing accuracy over the preceding centuries. The implication was staggering. Light, the very phenomenon that had puzzled humanity for millennia, was not just a wave, it was an electromagnetic wave. The luminous riddle had found its answer. The colors of the rainbow, the warmth of the sun, the flash of lightning, all were manifestations of oscillating electric and magnetic fields. Light was just one small part of a vast electromagnetic spectrum, which included radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays, all traveling at the same cosmic speed. This revelation had another profound consequence. If light was an electromagnetic wave capable of propagating through empty space by its own self-sustaining dance, then the mysterious luminiferous ether was no longer needed. The paradox was resolved. The cumbersome, contradictory medium that had burdened the wave theory for so long could simply be discarded. The universe became simpler, yet more profound. Maxwell's work was a triumph of theoretical physics, demonstrating the immense power of mathematics to not only describe nature, but to predict its hidden workings. It was a bridge between the visible and the invisible. The unification of electricity and magnetism and the identification of light as an electromagnetic phenomenon laid a new and robust foundation for physics. It set the stage for even more revolutionary discoveries. Yet one part of Maxwell's discovery would continue to echo, challenging our very understanding of space and time: the universal, unvarying speed of these electromagnetic waves. This constant, this cosmic speed limit, held secrets that would soon unravel the fabric of reality itself. Maxwell's equations had unveiled a profound truth. Light was an electromagnetic wave traveling at an astonishing and constant speed. But this very constancy, while elegant, created a new, unsettling question for the scientific minds of the late 19th century. Even with light's electromagnetic nature confirmed, the idea of the luminiferous ether persisted. For waves, a medium seemed indispensable. Sound needed air, water waves needed water. So surely, light waves needed their own cosmic ocean. This assumed ether had to be a marvel of contradictions, rigid enough to support light's immense speed, yet utterly intangible, offering no resistance to planets and stars as they sailed through the cosmos. Classical physics, built on Newton's sturdy foundations, taught that speeds were relative. If you walked on a moving train, your speed relative to the ground was different from your speed relative to the train. It logically followed that if Earth moved through this stationary ether, the speed of light measured on Earth should vary. Light traveling with the ether wind would appear faster, and against it, slower. Detecting this ether wind became a paramount goal. It was a chance to finally grasp the invisible medium of the universe, to measure Earth's absolute motion through space. Among those driven by this quest was Albert Michelson, an American physicist renowned for his meticulous measurements, especially of the speed of light itself. His precision was legendary. Michelson had already made attempts to measure the ether's influence, but his early apparatus lacked the sensitivity needed to detect such a subtle effect. The predicted difference was incredibly small. To achieve the necessary precision, Michelson joined forces with Edward Morley, a chemist and physicist at Case Western Reserve University. Together, they planned an experiment of unprecedented sensitivity. Their instrument, an interferometer, was a marvel of optical engineering. It was designed to split a single beam of light, send the two resulting beams along different paths, and then recombine them. If the two light beams traveled at slightly different speeds or for slightly different durations, their waves would be out of phase when they recombined. This would create an interference pattern. The idea was simple: align one light path with Earth's motion through the supposed ether and the other path perpendicular to it. The ether wind should then cause a measurable time difference. Even a minuscule difference in the speed of light along these paths, caused by Earth's velocity through the ether, would manifest as a shift in the delicate interference pattern. To detect such a subtle shift, the apparatus had to be incredibly stable, isolated from even the slightest vibrations. Any tremor could obscure the tiny effect they sought. Their solution was brilliant. They mounted the entire interferometer on a massive stone slab, which in turn floated in a circular trough of mercury. This allowed for smooth, frictionless rotation. By rotating the apparatus, they could ensure that if an ether wind existed, they would eventually align the interferometer arms both with and against it, and perpendicular to it, at various orientations. A bright lamp, carefully positioned, provided the light source. The beam was directed towards a partially silvered mirror, the beam splitter, which was the heart of the setup. One beam traveled to a mirror at the end of its arm, reflected back, and passed through the beam splitter. The other beam went to a mirror on its perpendicular arm, reflected, and then also passed through the splitter. The two beams, having traveled their separate journeys, were then recombined and directed towards a telescope where the interference fringes would be observed. They fully expected to see a shift in the fringe pattern as the apparatus was rotated, a clear signature of Earth's motion through the stationary ether. The summer of 1887 saw Michelson and Morley meticulously conducting their experiments in a basement laboratory, shielding their delicate instrument from temperature fluctuations and vibrations. Hour after hour, they carefully rotated the heavy stone slab, observing the interference fringes through the telescope, searching for any sign of the predicted shift. They recorded their observations with painstaking detail. Each rotation, each subtle movement was documented, cross-referenced, and analyzed for the telltale signs. The theoretical calculations predicted a small but definitely measurable shift. They knew it wouldn't be dramatic, but it should be there, a subtle dance of light and ether. But as the days turned into weeks, a puzzling pattern began to emerge, or rather, a lack of pattern. The fringes remained stubbornly still. They refined their methods, increased the path length of the light beams using multiple reflections, and ensured even greater isolation from external disturbances. Yet, the result remained unchanged. No matter how they oriented the apparatus, no matter how precise their measurements, there was no detectable difference in the speed of light in different directions. The ether wind that should have been blowing past Earth, causing light to travel at varying speeds, simply wasn't there. It was as if Earth was stationary in the ether, or the ether itself was moving with Earth. This was a profound contradiction. If the ether existed, Earth must be moving through it, yet the experiment showed no evidence of this motion. The very foundation of their hypothesis was crumbling. The null result sent ripples of unease through the scientific community. It was not just a failed experiment, it was a challenge to the very fabric of classical physics. Many tried to explain away the result. Perhaps the Earth dragged the ether with it, but this contradicted other astronomical observations. Perhaps the ether contracted objects moving through it. Indeed, physicists like Lorentz and Fitzgerald proposed that objects moving through the ether would contract in the direction of motion, precisely canceling out the expected fringe shift. It was an ingenious, if ad hoc, solution. However, these explanations felt like patching a leak rather than understanding the ocean. The constant speed of light, stubbornly refusing to vary, was more than an anomaly. It was a crisis for classical physics. For decades, physicists had relied on the concept of absolute space and absolute time. The Michelson-Morley experiment now forced them to question these deeply held, intuitive notions. The speed of light, c as it became known, was not merely fast, it was universally constant. No matter how you moved, no matter your frame of reference, light always approached you at the same, unchanging speed. This implied something profound. Light did not need an ether. It was a self-propagating entity, and its speed was an intrinsic property of the universe itself, a cosmic speed limit. The ether, that invisible, paradoxical substance, was finally rendered unnecessary. Its elegant demise paved the way for a more radical, more beautiful understanding of reality. The null result of Michelson and Morley was not a failure. It was a triumph, a signpost pointing towards a completely new way of understanding space, time, and motion. The universe had whispered a secret. The speed of light was absolute. Now it waited for a mind bold enough to accept this truth and to rebuild physics from the ground up, embracing this cosmic constant. This unyielding pace of light would soon lead to the most profound conceptual shift in physics, challenging our very perception of reality. Join us next time as we meet the scientist who dared to dream in 4 dimensions. The universe had whispered a secret. The speed of light was absolute. This truth, so simple yet so profound, echoed through the halls of physics, awaiting a mind daring enough to fully grasp its implications. That mind belonged to a young man named Albert Einstein. He wasn't a man of grand experiments in bustling laboratories, but rather a master of thought experiments. His laboratory was his mind, his tools, the keen edge of logic and imagination. While working at the patent office in Bern, Switzerland, he wrestled with the contradictions left by Maxwell's equations and the Michelson-Morley result. The constant speed of light was a stubborn fact. He often imagined what it would be like to ride alongside a beam of light. If he could match its speed, what would he observe? Would the light wave appear frozen, a static ripple? Classical physics suggested that if he moved at the speed of light, the wave should indeed appear stationary. Yet, Maxwell's equations described light as a dynamic, propagating wave, never static. This thought experiment highlighted a deep conflict. Either Maxwell's equations were wrong for moving observers, or something fundamental about space and time was misunderstood. Einstein chose to accept the unwavering constancy of light's speed as a fundamental principle. He dared to build a new framework upon this seemingly impossible truth. In 1905, in what he called his miracle year, he published his theory of special relativity, built upon two simple yet revolutionary postulates. The first postulate was the principle of relativity. It stated that the laws of physics are the same for all observers in uniform motion. This meant that whether you're in a stationary room or a smoothly moving train, the fundamental rules governing how things behave, gravity, electromagnetism, mechanics, remain identical. There is no absolute rest frame in the universe. All inertial frames of reference, those moving at a constant velocity, are equally valid. This idea wasn't entirely new. Galileo and Newton had applied it to mechanical laws, but Einstein extended it to all laws of physics, crucially including Maxwell's equations of electromagnetism. This extension was critical because it meant that the speed of light derived from Maxwell's equations must also be the same for all observers, regardless of their motion. And so the stage was set for the second, truly radical postulate, the constancy of the speed of light. The second postulate declared that the speed of light in a vacuum, denoted by c, is the same for all inertial observers, regardless of the motion of the light source or the observer. This directly contradicted our everyday intuition. If you throw a ball forward from a moving train, its speed relative to the ground is the sum of your throwing speed and the train's speed. But light does not behave like a ball. If you shine a flashlight from that same moving train, the light beam still travels away from you at precisely c, no faster, no slower relative to any observer. This postulate was a direct acceptance of the perplexing null result of the Michelson-Morley experiment. It wasn't that the experiment failed, it was that our understanding of reality was incomplete. If the speed of light is a universal constant, an unyielding cosmic speed limit for everyone, then something else must be flexible. That something else turned out to be space and time themselves. Our measurements of distance and duration, once thought to be absolute and universal, now had to be relative, dependent on the observer's state of motion. This was the gentle revolution. It wasn't about denying observations, but about reinterpreting them through a radically new lens. The very fabric of reality was about to shift. One of the most profound implications was the relativity of simultaneity. We intuitively believe that two events happening at the same time are simultaneous for everyone. Imagine a long train moving at a very high, constant speed. Lightning strikes the front and back of the train at what a stationary observer on the ground sees as the exact same moment. For the observer on the ground, standing precisely halfway between the strike points, the light from both flashes reaches them simultaneously. They conclude the strikes were indeed simultaneous. Now consider an observer standing exactly in the middle of the moving train. As the light from the front and back flashes travels towards them, the train itself is moving. Because the train is moving forward, the observer on the train moves slightly towards the light coming from the front and slightly away from the light coming from the back. Therefore, the light from the front flash reaches the observer on the train before the light from the back flash. For this observer, the events are not simultaneous. This was a truly astonishing conclusion. Two observers, both equally valid, could genuinely disagree on whether two events happened at the same time. Simultaneity was relative. There is no universal, absolute now that applies to everyone in the universe. What is now for you depends on your motion. This shattered the Newtonian concept of time as a universal, unchanging river flowing uniformly for all. Time, like space, was intertwined with motion. This led to the concept of time dilation. Clocks moving relative to an observer run slower than clocks at rest relative to that observer. Similarly, objects moving relative to an observer appear to be shorter in the direction of their motion than when they are at rest. This is called length contraction. These are not mere optical illusions. They are real, measurable effects of relative motion, consequences of the universe's unwavering commitment to the speed of light. Einstein's insights revealed that space and time are not separate, independent entities. Instead, they are deeply interwoven, forming a single, unified fabric. This four-dimensional continuum, combining 3 dimensions of space and 1 dimension of time, is known as spacetime. It is the stage upon which all cosmic events unfold. Spacetime is not a rigid, unchanging backdrop. It is dynamic, responsive, and its geometry is influenced by the presence of mass and energy. The constancy of the speed of light is the bedrock of this new understanding. It is the ultimate speed limit, a fundamental constraint on how information and matter can travel. Einstein's special relativity broke free from the absolute space and time of Newton, offering a more nuanced and accurate description of reality, especially at high velocities. It provided a new foundation for understanding motion, energy, and the very structure of the universe, moving beyond the need for a mysterious ether. But special relativity only dealt with uniform motion. What about acceleration and the force that governs the cosmos, gravity? How would this new fabric of spacetime respond to the heavy hand of mass? The answers would reveal an even deeper reshaping of reality. Einstein's postulates, so elegantly simple, began to reveal a universe far more pliable than anyone had imagined. The unwavering speed of light demanded that space and time themselves adjust. Our intuitive understanding of time as a universal, unvarying flow was challenged. Instead, time was found to be relative, its passage dependent on motion. This led to the concept of time dilation. For an observer watching a clock moving at a significant fraction of light speed, that moving clock would appear to tick slower. It's like watching a gentle river flow. If you are standing on the bank, the river passes at a certain rate, but if you are drifting with the current, your perception of its speed changes. The faster an object moves, the more its internal clock, its processes, its aging slows down relative to a stationary observer. This isn't an illusion, it's a fundamental shift. Every second for the moving object is a slightly longer second for the observer at rest. Time itself stretches, accommodating the constant speed of light. This effect, though imperceptible in our daily lives, becomes pronounced at speeds approaching the cosmic limit, revealing time's true flexibility. Similarly, space itself undergoes a transformation. The concept of length contraction describes how objects moving at high speeds appear shorter. An object in motion observed from a stationary frame shrinks in the direction of its movement. Its length contracts, much like a shadow compressing as the light source shifts. Imagine a spaceship traveling at immense speed. For For an observer on Earth, that spaceship would appear squatter, shorter along its direction of travel. Again, this is not an optical trick. It is a genuine physical change in the object's measured dimensions, a direct consequence of its velocity. These effects, time dilation and length contraction, are inextricably linked. They are the universe's way of ensuring that the speed of light remains constant for all observers. If time and space didn't adjust, the speed of light would vary, contradicting the very foundation of special relativity. These profound insights led to an even deeper understanding. Space and time are not separate entities, but two facets of a single, unified whole. This is the spacetime continuum, a four-dimensional fabric where three dimensions are space and the fourth is time. All events unfold within this cosmic weave. Every object, every event exists as a world line within this spacetime. Our journey through space is always accompanied by a journey through time. The faster we move through space, the slower we move through time, and vice versa. It is a constant, delicate balance governed by the speed of light. The unification of space and time into spacetime was a conceptual leap, forever changing how we perceive reality's fundamental structure. It transformed our understanding from a rigid, absolute stage to a dynamic, interwoven tapestry, responsive to the presence of matter and energy. But these aren't just theoretical curiosities. The predictions of special relativity are not only measurable but are essential for everyday technologies. Perhaps the most familiar example of relativistic effects in action is the Global Positioning System, or GPS, that guides our journeys. GPS satellites orbit Earth at high speeds, about 14,000 kilometers per hour, and at significant altitudes. Because of their speed, the clocks on these satellites experience time dilation. They tick slightly slower than clocks on Earth's surface. If these relativistic effects were not accounted for, the precise timing signals sent by the satellites would be off by many microseconds each day. This seemingly tiny discrepancy would accumulate rapidly, leading to errors in position measurements of several kilometers per day. Without Einstein's relativity, our GPS devices would quickly become useless. Every turn-by-turn direction, every accurate location, silently confirms his theory. Beyond everyday technology, the cosmos itself provides dramatic evidence of time dilation. Consider subatomic particles called muons. Muons are created high in Earth's atmosphere when cosmic rays collide with air molecules. They are unstable and have a very short lifespan. In their own reference frame, muons exist for only about 2 microseconds before decaying into other particles. This is their proper time. Even traveling at nearly the speed of light, classical physics predicts they shouldn't have enough time to reach Earth's surface before decaying. Yet countless muons are detected at ground level every second. They survive much longer than expected. This extended lifespan is a direct consequence of time dilation. From our perspective on Earth, the muons' internal clocks are ticking slower. Their journey through spacetime is stretched, allowing them to traverse distances that would be impossible within their proper lifetime. The evidence is clear: time and space are not fixed but dynamic. They flex and yield to accommodate the universe's ultimate speed limit. This cosmic weave, this spacetime, is the stage upon which all events unfold, its properties intimately connected to motion and speed. Special relativity provided a new, accurate lens through which to view motion at high velocities, revealing the true nature of duration and distance. It was a profound reimagining of reality built on the simple yet revolutionary principle of light's constant speed. The universe, once thought to be a static stage, was shown to be a vibrant, responsive entity, where our measurements are always relative. This understanding, confirmed by both everyday technology and cosmic phenomena, laid the groundwork for even deeper revelations about the universe. For special relativity only described uniform motion. What about the immense force of gravity and how it might warp this flexible spacetime? The answers would reveal an even more astounding cosmic truth. Our journey through the cosmic weave has shown us that space and time are not fixed. They stretch and bend, accommodating the universe's unwavering commitment to the speed of light. This constancy is more than just a number for how fast light travels. It is the universe's ultimate speed limit, a fundamental barrier for anything with mass. To accelerate any object with mass to the speed of light would require an infinite amount of energy. The closer an object gets, the more energy it needs, infinitely so. As an object gains speed, its mass effectively increases, demanding ever more force to push it further. It's a cosmic speed wall built into the very fabric of existence. Only particles without mass, like photons themselves, can travel at this ultimate speed. They are born at sea and forever move at sea. This cosmic speed limit isn't just about how fast things can move. It's about preserving the fundamental order of the universe, causality. Causality dictates that a cause must always precede its effect. The universe, in its intricate dance, maintains this logical flow at all costs. If something with mass could somehow travel faster than light, it would break this sacred rule. Effects could happen before their causes. Imagine sending a message or even an object faster than light. It could, in principle, arrive at its destination before it was even sent from another observer's perspective. This would unravel the very fabric of reality, creating paradoxes that the universe seems inherently designed to prevent. The speed of light is its guardian. To understand this better, we can visualize events in spacetime using a concept called the light cone. For any event, a light cone defines what is its past, what is its future, and what is its elsewhere, events that cannot influence it, nor be influenced by it. Imagine an event happening right now at a specific point in space and time. This event is at the apex, the tip of our light cone. The lower cone represents your past light cone. All events within this cone are those from which light or any influence could have reached you. These are your potential causes. The upper cone is your future light cone. All events within this cone are those you can influence, those that light or any signal from you can reach. These are your potential effects. Events outside both cones are in your elsewhere. They are too far away in space and too close in time for any signal to have reached you or for you to reach them. The light cone is a geometric representation of causality. It ensures that cause and effect always remain in their proper order. No information, no matter, no energy can ever travel from an event outside your past light cone to you, nor from you to an event outside your future light cone. This means our concept of a shared, universal present moment is an illusion. What is now for one observer might be past or future for another, depending on their relative motion. The light cone defines the boundaries of what is real and accessible to us, shaping our perception of here and now in a profound way. This cosmic speed limit has profound implications for our dreams of interstellar travel, making the vastness of space even more daunting. Even at the speed of light, crossing the immense distances between stars takes years, decades, or even millennia. Our closest stellar neighbor, Alpha Centauri, is over 4 light-years away. A journey there at light speed would take over 4 years. While a traveler moving near sea would experience time dilation, making their personal journey shorter, millennia would still pass on Earth. The energy required to accelerate a spacecraft, even a small one, to a significant fraction of light speed is astronomical, far beyond our current capabilities. The allure of faster-than-light travel, or FTL, remains a staple of science fiction, allowing characters to traverse galaxies with ease. However, within the framework of our current understanding of physics, FTL travel for anything with mass remains impossible. The constant speed of light is not just a constraint, it is a fundamental property that defines the very structure and behavior of the universe. It dictates our perception of now and here, intertwining them with our motion and the universal constant. This cosmic speed limit reveals an intricate, interconnected tapestry of existence, where every event is linked to others within the boundaries of light. Time is not a universal clock, but a personal journey. Its passage is deeply entwined with our speed and the gravitational fields we inhabit. Space is not an empty, rigid stage, but a dynamic, flexible medium that contracts and expands based on motion and mass. Our journey began with the elegant equations of Maxwell, unifying electricity and magnetism and revealing light's electromagnetic nature. Einstein, with his thought experiments, dared to accept light's constant speed, reshaping our understanding of space and time. And later, general relativity showed us how massive objects bend this spacetime fabric, creating the force we know as gravity. The universe, in its elegant simplicity, is far more wondrous and intricate than our everyday senses first perceive. From ancient fires to precise interferometers, from the genius of Maxwell to the profound insights of Einstein, patience and observation have guided us. The speed of light stands as a testament to the universe's order, a constant that shapes everything we know and everything we can ever hope to know. It reminds us of our place within this vast, interconnected cosmic tapestry, forever bound by its fundamental rules, yet forever curious. And so, as the moon climbs high, casting its gentle light upon a world forever shaped by these truths, sleep well and dream of the mysteries that still await our discovery.